Hello everyone, welcome to the 7th lecture of our Introduction to Modular Forms. So last time we proved that the space of modular forms of weight k, that is denoted by m sub k, is finite dimensional. And also we proved like the dimension formula, that is the dimension of mk is given by floor of k over 12 when k is 2 mod 12 and floor of k over 12 plus 1 when k is not 2 mod 12. Of course, this is for like even k, even non-negative k, right? And we have seen that for, obviously for odd k, the only modular forms of weight odd are the constant zero function, and last time we proved that the only modular forms of negative weights are also the constant zero functions, right? Yeah. Also, we have seen a basis of mk. So, and that basis is called Eisenstein basis. Eisenstein basis, and that basis is basically the set of all the E4 to the A, E6 to the B, where 4A plus 6B equals to K. So this is the basis of MK. Okay, yeah. So, so today we start with an observation. So I think I've mentioned it in one of the previous lectures that, well, if f is a modular form, then we can write f as the Q series expansion, right? And there are infinitely many coefficients in this Q expansion. But f belongs to a finite dimensional vector space. So it's natural to guess that, well, if we know only finitely many coefficients, then we can uniquely determine the modular form, right? And in fact, that guess is correct. And well, let us state it. Proposition that says that for every k greater than 0, there exists some r such that the first are Fourier coefficients. So these an are called Fourier coefficients. Fourier coefficients uniquely determine f, that is the modular form. So in other words, if we have two modular forms such that their first r Fourier coefficients are the same, then the two modular forms are in fact the same. In other words, if f of z is equal to sum of an qn and g of z is equal to sum of bn qn, and ai equals bi for all I beings I from 0 to r, then f equals to g. So the proposition states that for every k, we can find such an r. Okay, so let us try to prove it. So for this proof, we shall define a linear map. That linear map is, let's say, Lj, and this is from the space of modular forms of weight k to Cj. And it takes a modular form f, and of course f can be written as sum of an qn, and it maps f to, and the function Lj maps f to the j tuple given by a0 up to aj minus 1. Okay, and you can easily check that this is the linear map. Then let's take the kernel of Lj. So, yeah. And my claim is that kernel of Lj plus 1 is a subspace of kernel of Lj. Why is that? Because if we take any modular form from kernel of Lj plus 1, then that modular form has A0 up to Aj, all are equal to 0. Right? So then obviously A0 up to Aj minus 1, that is also the 0 vector. Right? So yeah, kernel of Lj plus 1 is a subspace of kernel of Lj. So that means this sequence, let's say kernel of L1, kernel of L2, kernel of L3. So this is a decreasing sequence, right? And yeah. And so therefore, if we take the sequence of natural numbers that is given by dimension of kernel of Li, okay, this sequence is a decreasing sequence. So is decreasing, and of course this decreasing sequence is in the set of natural numbers, right? So therefore this sequence must stabilize at some point. So let the stabilizing point be R, and well, you guessed it, that R is the R of our, we need to show. Yeah. So yeah, so since it's decreasing, at some point it will stabilize. So there exists some R such that dimension of kernel of Lj is equal to dimension of kernel of Lr for all j bigger than or equal to R. Okay. And yeah, and all these kernel of Lj are subspace of kernel of Lr, right? And they have the same dimension. So this means kernel of Lj is in fact equal to kernel of Lr. Okay, yeah. Now, well, we claim that this R is our desired R. So let us take a modular form from kernel of Lr. Okay. We need to basically show that f is 0. So assume for the sake of contradiction that f is not 0. Then, well, since f is not 0 and f is in kernel of Lr, that means the Q expansion of f looks like this. So the first R coefficients are 0. Then, so A R Q to the R plus so on and so forth. Okay, and well, since f is in kernel of Lr, that means all these coefficients are 0, right? And also we assume that f is not 0. That means there is some coefficient that is non-zero. So suppose R prime is the smallest, such that A R prime is not 0. Right? Then of course R prime is bigger than R. Right? Then what about L R prime plus 1 of F? So this L R prime plus 1 of F is given by, well, A0 dot A R prime, right? And A R prime is non-zero, so this is not 0. So therefore F is not in kernel of L R prime plus 1. But we know that this is a subspace of kernel of LR, since R prime is at least R, right? So this is a contradiction because F is in kernel of LR. So this is a contradiction, therefore F must be 0. So we have proved that if the first R coefficients are 0, then the modular form is 0. Then suppose we have two modular forms as before. There is an, qn. Of course, there's a sum. And g of z is sum of bn, qn. And it has first r coefficients are equal. So that means, yeah, ai equals to bi for all I smaller than or equal to r minus 1. Okay, so then this tells us that f minus g, if we take this modular form, it has first r coefficients 0. Therefore, f minus g is 0. So f is equal to g. So if we have the first r coefficients to be equal, then the two modular forms have to be equal. Okay. Does anyone have any guess for what the value of r can be? Of course, r depends on k. So what is r? R is the smallest number such that knowing the first r Fourier coefficients are enough to uniquely determine the modular form. That's a very good choice. So yeah. So r is dimension of mk. So does it work? Well, probably it does. Let's find out. So yeah, in fact, it does work. And in order to prove that, we need to prove a formula that is called the valence formula. So what is the valence formula say? The valence formula say that, well, let's say f is a non-zero complex holomorphic function on the upper half plane. So, and it's holomorphic on the upper half plane. And well, we are stating the valence formula in its most general scenario. So we could have said that, well, f is a modular form. That's a very special situation, right? So yeah, let's say f is a non-zero holomorphic function on the upper half plane, and f is weakly modular of weight k. What this means is that, well, we know that f of az plus b over cz plus d is equal to cz plus d to the power k f of z. So this condition is called weakly modular of weight k. And well, in order to be modular form, we need that f is bounded as the imaginary part goes to infinity. So we are not requiring that condition right now. So f can have a pole at infinity. Then, well, let's first state it, then I'll explain what these terms mean. V infinity of f plus half, V I of f plus 1/3, V omega of f plus the sum of Vz of f, where z is in the fundamental domain, and of course z is not equal to I or omega, is equal to k over 12. So what these V's mean? So Vz of f basically means that it's the order of 0 of f at z. Order of 0. Well, some people say just order of 0 of f at z. So that means suppose f is a meromorphic function. Well, for simplicity, we can first say that f is a holomorphic function. Holomorphic function around the point z. Then f has the power series near z, right? So f of w is equal to sum of w minus z to the power n. Here I have an. Okay, so this Vz of f denote the first coefficient that is non-zero. So if the first coefficient that is non-zero is, let's say ak is the first coefficient that is non-zero. That means all the coefficients from a0 up to ak minus 1, all of them are zero, right? So if ak is the first coefficient that is non-zero, we can factor out w minus z to the power k here, right? ak, sorry, should be an w minus z to the power n minus k. And this sum runs from n equals to k to infinity, right? And this k is the order of zero of f at z. Okay. And yeah, and if f has a pole at z, then we no longer have a if f has a pole at z, then we no longer have a power series, rather we have a Laurent series. Okay. Then near well, I shouldn't really say near z, because the Laurent series is defined in an annulus, right? So in an annulus centered at z, we have f of w is given by sum of an w minus z to the power n. Yeah, and here as well, since f has a pole at z, then n starts at some negative integer, right? So this negative integer is called the order of pole. And yeah, and in fact, this is the value of vz if f has a pole at z. Yeah. Yeah. So if we summarize, then it's positive if f has a 0 at z. It's negative if f has a pole at z, and it's 0 otherwise. So if z is neither 0 nor a pole, then this is just 0. Okay, and it's positive if f has a 0, and then it denotes the order of the 0. It's negative if f has a pole, and yeah. Okay. Yeah, but how do we compute this thing? So there's a very beautiful formula to compute this number. Of course, this is an integer, right? And this integer is given by this integral 1 over 2 pi I integral of f prime of z over f of z dz. And this integral is done over gamma. And what is gamma? Gamma is a circle centered at z. Well, does any circle centered at z works? Unit circle? Okay. Well, not really unit circle. Well, the radius of the circle doesn't really matter, right? We need an extra condition, and that extra condition is that like gamma does not contain any 0 or pole at the interior. So if, let's say, this is z, this is a 0, then or a pole, then we need to choose a circle in such a way that in the interior there is no 0 or pole. Well, yeah, this is you need to use residue theorem to prove that this works. Yeah. Well, also, if let's say the 0 or pole at z is of order m, so let's say this is of order m, where m now can be any integer. If it's negative, then f has a pole at z. If it's positive, f has a 0 at z. Okay. Then like we can write f of w as sum of an w minus z to the power n, but n starts from m. right? And of course, AM is non-zero. Then f prime of W over, yeah, I probably shouldn't have written Z here because, yeah, Z is, yeah, sorry. Yeah, then f prime of W over f of W, this can be written like this. So what's the differentiation of the first term here? It's M A M, then W minus Z to the power M minus 1. And the first term here is AM W minus Z to the power M, right? So, yeah. So this can be written as M over W minus Z plus another holomorphic function. And if we integrate it, so if we integrate it over gamma, then we get that this is integration of 1 over W minus Z dz, so dw plus integration of gw. Okay. And this integral is 0. Why is this 0? Because we basically required that f doesn't have any 0 or pole in the interior of gamma, right? So that forces us to this, where G does not have any 0 or pole in the interior of gamma. So this integral goes to 0. And this, we know the value of this integral, right? This is m 2 pi I. And if we divide by 2 pi I, so 1 over 2 pi I f prime of W f of W dW is equal to m. So this is a very short proof of why this integral works as the order. Okay. And also in many textbooks you'll see that this term they'll call as valence of f. Valence of f at z. So that's why our formula gets the name valence formula. Okay, so let us get back to the statement. Yeah, so we have defined what is Vz and Vw, Vi, similar way. Then what is this thing? So we defined how to compute order or valence at a point, right? But this is infinity. So how do we define the valence at the point of infinity? Well, the answer is, so given f, we can define f tilde, right? F tilde of q is defined as f of e to the 2 pi I z. Sorry. So I wrote it wrong. F tilde of e to the 2 pi I z is equal to f z. So the way we define the q series, right? And f tilde is defined where? F tilde is a function on the unit disk, right? Unit disk to C. Right? Then what is f tilde of 0? So this was f of I infinity, right? So and this was finite when f is a modular form. But f is no longer a modular form. So we relax this condition. So f is now a meromorphic form. And yeah, and this is not necessarily finite for our case. But nevertheless, we define v infinity of f as v0 of f tilde. So f tilde is a holomorphic function, and that is defined on the unit disk. Well, unit disk except the origin maybe. if f has a pole at the origin, if f tilde has a pole at the origin, then yeah. So, and we can compute the order of the pole at 0 of f tilde, and that the value we get is defined as this v infinity of f. All right. Yeah. So let us like write the valence formula again. Then we'll get to prove it. V infinity of f plus half of vi of f plus 1/3 of v omega of f plus sum of vz of f, where z is in the fundamental domain and z is neither I not omega, is equal to k over 12. But I is the square root of -1 and omega is the third root of unity. This one. Well, here's a very interesting observation. So omega is third root of unity. I is fourth. So these these two numbers, 3 and 4. So these two numbers like come up very often in the study of modular forms. And in fact, so the LCM of 3 and 4 is 12. So we can see a lot of occurrences of 12 in the study of modular form. In the dimension formula, we saw a mod 12 condition. In the valence formula, there's a 12. And I think there was a very nice explanation of it why 12 occurs. So 12 comes up way many times, too many times. And that is, what is our modular group we are working in? We are working in the modular forms over SL2Z, right? And SL2Z is generated by S and T. What is S? S was, yeah, this is T and this is S, right? So T has order 4, but S has infinite order, right? And if SL2Z is generated by S and T, then it's generated by ST and T as well, right? T has order 4, but ST has finite order. In fact, if I remember correctly, ST has order 6. So SL2Z is in fact generated by two elements of finite order. And what's the LCM of these two orders? It's 12. Yeah, yeah. 4 and 6 are of course related to Eisenstein basis. Like E4 and E6, like they make up the whole universe of modular forms. Yeah. Okay, that was an interesting observation. And yeah, now we'll prove the balance formula. So let's draw the fundamental domain. So this is negative half, this is half, and this is I, this is omega, this is omega plus 1, right? So these are fundamental domain, and yeah, and we will construct a contour over which we will integrate some function. Okay, and the function we will be integrating over is f prime of w over f of w over some contour C, and now we will define this contour. Okay, so our contour goes like this. So this is w, this is say w plus 1. Sorry, omega plus 1. My w and omega looks the same. This is say I. And yeah. let's say at some very big height t, then yeah, we'll ignore w and w plus 1. Then again, so this is the contour we are integrating over. And how is this contour defined? It's defined as, well, let's say these little circles are of very small radius epsilon. And well, first we draw the fundamental domain, then we cut out very little circles. Sorry? Yeah. But what if we have some zeros on the side? Let's say if we have a zero here, what do we do? Because in order to integrate over this function, we need to have that this function has no zeros or poles in the contour we are integrating, right? So let's say if there is zero here, what we do is that we again cut out a very little very little semicircle here. Yeah. And well, let's say if this point is p, this is p plus 1. Our function is weakly modular. So it has period 1, right? So if p is a 0, so is p plus 1. So we are taking exactly one of them. We are taking p and ignoring p plus 1. Okay, so okay, this is done. But what if we have a 0 here? If we have a 0 here, we also have a 0 here as well, right? Why? Yeah, if this is, let's say, z, this is negative 1 over z. And we know that f of negative 1 over z is equal to z to the kf of z. If z is a 0, then so is negative 1 over z. Then again, we take exactly one of them. So we ignore this and take this. Okay, yeah. And as t goes up to infinity, limit of t goes to infinity, integral over, let's say this is c f prime of over f. Yeah. Okay, and what is this sum? So this sum is actually 2 pi I sum of Vz of f, where z is in the fundamental domain and z is not equal to I or omega. So basically, we can consider this very large contour to be small contours around the zeros or poles, because only those terms are contributing to this sum, right? The points that are neither pole nor zero, they are contributing 0. Okay, so yeah. So if this is a 0 or a pole, and this is 0 or a pole, this is 0 or a pole, so on and so forth, then essentially we can like transform this contour as the sum of these three contours. Okay. Yeah, so we have almost everything. Well, we only have the first term here, right? Okay. So we got the first term. That's the progress, I guess. And yeah, I have to draw the contour again. Can someone tell me why the vertical lines cancel each other? Hmm? Yeah, they have the same value but different orientation. Exactly. Okay, so A, B, C. No, this is D. E, F, G, H. So let us orient this counterclockwise. So yeah, so integral over AB plus integral over GH is equal to 0 because they have the same value but different orientation. Okay, yeah, that's cool. But what about this horizontal line HA? So what is integration over HA? Of course, the function is f prime by f. So I'm not writing the function. So let's try to compute that. Can someone guess what that term might be in our balance formula? Exactly, because this VI and VW are coming from these little semicircles. Okay, so ideally this term should be V infinity. So let's check if that's correct. Okay, yeah, and the HA can be parameterized as this is T and this is IT plus half, right? And this is IT minus half. So we can parameterize HA as, let's say, rho of T, where T is negative T plus I capital T, and T is from negative half to positive half. Okay. So this is a way to parameterize HA. Now let's have a look at the Q expansion. So we define f of z as f tilde of q, right? And let's not forget that q is e to the 2 pi I z. Then what is f prime of z? F prime of z is nothing but f tilde prime of q dq dz, right? And if we divide by f of z, then we get that f prime of z, f of z dz is equal to f tilde prime of q, f tilde of q dq, right? So we can integrate. Integrate over HA, f prime by f is equal to HA is equal to integral over, well, HA is essentially this, like rho of t. And this is integral of f tilde prime over f tilde. And this, what is this integration contour? This is just q of rho of t, right? So, and rho of t is negative t plus I t, right? So what is the image under Q? Image of HA under Q? This is e to the negative 2 pi t, e to the 2 pi I t, that's a minus sign, right? Yeah. And what is this? This is a circle centered at the origin with radius e to the negative 2 pi t. And it's oriented clockwise or counterclockwise? Hmm? Counterclockwise. Well, we have a minus sign here. What does that mean? That means we are going clockwise. Right? So what should this be? This is minus sign for the orientation, and this is V0 of F tilde. And what is this? This is V infinity of F. Right? Is that clear? So yeah, we got one part. Now now we need to find what the BC arc, FG arc, DE arcs are contributing. And after that, we need to somehow take care of this CD and EF here. Okay. So yeah, let's check out. So we have got this term. That's very nice. We have also got this term. So and we have to get these three terms, right? Yeah. Also, a slight detour, that is, let's say I'm integrating 1 over z over some curve gamma. And now gamma is not the whole unit circle. Gamma, let's say gamma is just half of the unit circle. So can someone tell me what the integral should be? So if gamma is just the half of the unit circle. So we know that if gamma is the whole unit circle, then this integral is 2 pi I. What if gamma is the half unit circle? Pi I. Is that correct? Yeah, I think so. So let's try to do it. So how can we parameterize this curve? So this can be parameterized as well, without loss changes. Suppose that the radius is 1. So e to the I theta, where theta is from 0 to pi, right? So this integral essentially boils down to integral of 0 to pi. 1 over z is 1 over e to the I theta. And what is the differentiation of this thing? Over, so sorry, it should be IT. Yeah. And its differentiation is nothing but I e to the IT, this t. So this is I integral 0 to pi dt, and it's indeed pi I. So now, what if now it's not the whole semicircle, it's just a part of the semicircle? Then what would the integral be in terms of this angle? So, yeah, exactly. So if this angle is, let's say, theta, of course in radians, then this is theta I. So if we have the whole circle, the integral is 2 pi I. If it's a semicircle, pi I. And if the arc makes an angle of theta radians, we have integral pi I. Okay, and we are going to use this very fact to compute the integrals of the arcs BC, FG, and D. Yeah, does this theorem have a name? I remember someone referring it to as mouse hole contour lemma. Mouse hole contour lemma. I'm not sure if that's a widely used name, but okay. Yeah. So this is our omega. Okay, and this is the arc BC. And yeah, BC was oriented this way. Now, what is the integral over BC? So this integral over BC is essentially, well, it essentially boils down to m over z minus omega, right? Because we have seen that, where is it? Yeah, here. The integral essentially boils down to this. So instead of integrating over the whole circle, if we integrate over some part of it, then it should be m times the angle. Now, what is the angle it makes? Of course, we have to keep in mind that we are working in the limit as epsilon goes to 0. So now it's making a like very big angle. But if I like shrink the radius, then what angle does the arc make with with omega? Pi by 3. That's an excellent guess, and yeah, it's correct. No, is it pi by 3? Yeah, it's pi by 3. 6 degrees. Yeah. And of course, we need to divide it by 2 pi I, right? So if we divide it by 2 pi I, we get that 1 over 2 pi I. Also, what should be the sign, positive or negative? Uh, well, why should it be negative? Well, if you said positive, then also I would ask the same question. Like BC is part of a contour that is oriented counterclockwise. So in that sense, it should be positive, right? But if we look at BC alone, it's part of a circle that is oriented clockwise. So which one should we consider while evaluating just BC? Hmm? No, actually we don't. So, well, we say that, well, BC is a part of this circle, right? And if we orient BC this way, then this circle is oriented clockwise. Therefore, there's a negative sign. So this gives us negative V omega over 6. Right. And similarly, what was it? It was FG, right? FG was around omega plus 1. So similarly, we have 1 over 2 pi I integral over FG is given by negative V omega plus 1 is divided by 6. But these two are the same. Why are the same? No. It's not related to 1 by z. Yeah. Well, you're saying that the omega plus 1 is negative 1 over omega. Is that what you're trying to say? 1 over omega is this, and if we negate, yeah. Well, there's a very simple reasoning, and that is f is weakly modular, so f of omega is equal to f of omega plus 1. Not only that, if we take a neighborhood of omega and a neighborhood of omega plus 1, f is same in these neighborhoods. So why the valence should change? They're the same. Only f of omega equals f omega plus 1 doesn't guarantee that v omega is equal to v omega plus 1. Additionally, we have the very beautiful fact that in a neighborhood of omega and omega plus 1, f agrees. So that's why we have these two are the same. Because you see, the integral actually depends on like on the behavior of these points, and yeah, and in a suitable neighborhood, the behavior of these points and these points are the same. Yeah, that's a very nice point actually. Yeah, it illustrates the very fact that integral doesn't really depend on the value on the center. So if we add these two, we get that this term is equal to v of omega divided by 3. And this term was in our formula. And similarly, let's say this is I, this is omega plus 1. Okay. And if we take this semicircle here, and yeah, let's orient this because orientation is very important. So what does this not really semicircle, this arc contribute in the integral? B, C, it's DE, right? What is integral of f prime over f over DE? You can try to relate this with the previous ones we did. So what, like in the limit epsilon goes to 0, like epsilon means this radius, the radius of this arc. In that limit, what is the angle? Yeah, it's pi, right? In the limit, it's pi. So it should give us pi times the I of f, right? Pi I, sorry. Yeah. Yeah. Yeah, I was about to ask that. So what should be the sign, plus or minus? Although it's a part of a contour that is oriented counterclockwise, but if we complete the circle, that circle is oriented clockwise. So that's why we have a minus sign. And again, if we divide it by 2 pi I, we get the vi of f over 2. So we have everything except k over 12, right? And of course, the k over 12 terms, they are getting from this and this. Yeah. So essentially, we need to show that the integral over CD plus the integral over EF, and if we divide it by 2 pi I, we get k over 12. We just need to show this one, right? Okay. It should be minus. No, like k over 12 is on the other side of the equation. So, yeah, I think it's correct. Okay, can someone tell me how these two arcs are related? Reflection of one another. Yes, reflection about the imaginary axis. Okay, that's a very good answer. But in terms of matrices of SL2Z, like which matrix of SL2Z transform one of these to another? T. What was T? T is negative 1, 1. This, right? Yeah, T is the one that transforms CD to EF. But uh, there's of course a but. What about the orientation? Does the orientation stay the same, or it gets reversed, or what is it? Yeah, if I take a point here, T maps it here. If I have a point here, T maps it here. If I have a point here, T maps it here. So the orientation gets reversed, right? So essentially, then what we have is that, well, let's say this is gamma. So this is pi. Sorry, this is gamma. Integral of gamma minus integral of t gamma. Minus because the orientation gets reversed. So we need to compute this. Okay. In fact, we are going to show we are going to show a more general result. That general result is this. Should I state the general result now? Yeah, let's do it. G is any matrix of SL2Z. It's minus k gamma 1 over z plus d over c. And well, what is dc? Well, G is ABCD. And yeah, we need to of course remember that the function we are integrating over is f prime over f. Okay. It's really tiring to write the integrand all the time. So yeah, I'm kind of taking a shortcut. Okay. And what is f of gz? Well, by gz I mean that g acting on z. Right? And that is, we all know that our favorite formula. Right? And if we now differentiate with respect to z, we get that f prime of gz dgz over dz is equal to cz plus d to the power k f prime of z plus kc cz plus d to the k minus 1 f of z. Is that right? Then if we divide by f prime of gz, we get that f prime of gz, not g of z, gz, f of gz times dgz over dz is equal to, well, f of gz is equal to this, right? So we get f prime of z over f of z plus kc this, right? And then, yeah, a little bit of swapping variables, we get f prime of z, f of z dz minus f prime of gz, f of gz dgz is equal to negative k 1 over, well, where did I put in integration sign here? Z plus c over d. Right, did I make a mistake here? No, I hope it's there. Yeah. Then let's copy this line. Well, sorry? Which one is? Yeah, c by d. Sorry. D by c, right? Thank you. Yeah. Yeah, let's now copy this and integrate. Copy. And all these integrations are going to be over gamma. So this is integration over gamma minus integration over g gamma, right? Equals to negative k gamma 1 over z plus d over c. Now, in our very special case, we have our g is equal to t, which is negative 1, 1. So our d is 0, c is minus 1. So what is this? This becomes negative k integral over gamma 1 over z. Right? Now, what is gamma? Gamma is this one, right? Well, we could have taken this one as well. Doesn't really matter. Yeah. And now what is this integral? This is our origin. We have to remember. And this goes this way. So, yeah, and so this is going to be the angle it makes, right? What is that angle? So this is pi by 2, and this is what? 2 pi by 3. What is the difference? Two pi by 3 minus pi by 2 is equal to pi by 6, right? And the sign? Yeah, and it should be negative, right? So, and the negative here and the negative here cancel out each other. So we have k times pi by 6 I. And this is just the integral. Of course, we need to divide it by 2 pi I. So this is k pi I by 6 divided by 2 pi I. It's k over 12. Yay, finally we have our balance formula. Okay, now let us take a quick break of, let's say, 5 minutes, then we'll see how this balance formula becomes useful. All right, so we have proved the balance formula, and now we will prove that in the first theorem we have seen that there exists an R such that knowing the first R coefficient is enough. And now using balance formula, we shall prove that that R is exactly the dimension of the space of modular forms. So the theorem states that let F be a modular form of weight K, and well, then F can be written as, of course, the Q series. And suppose AI is 0 for every I up to D minus 1. What is D? D is the dimension of MK. Then F is 0. So proof, suppose, well, we have two cases, right? Like for the dimension, we have two cases, that K is 2 mod 12 and K is not 2 mod 12. So let's do the easier one. So suppose K is not 2 in mod 12. Then what is D? D is K over 12 plus 1, right? So yeah, and we have that from 0 to D minus 1, all the coefficients are 0. So that means f of z, which is actually f tilde of q, right? This sum starts from q to the d. Well, right. So then what is the order of 0 of f tilde? At least d. So that means v infinity of f is at least d, and d is what? This. D is k over 12 plus 1. And what is this? This is at least k over 12. And what is the valence formula? Valence formula was that v infinity of f plus vi of f by 2 plus v omega of f by 3 plus a sum of vz of f is equal to 12 by 3. Now, f is a modular form. So f is holomorphic on the upper half plane. So, yeah, so all these terms are non-negative, because the valence is negative only when the point is a pole, right? But if, since f is a modular form, f does not have any pole in the upper half plane. So these terms are non-negative. Therefore, why did I write 12 over 3? It should be k over 12. Sorry. Yeah. So, of course, so like v infinity of f plus some non-negative terms is k over 12. That means k over 12 is larger than or equal v infinity of f. Right? But here we have proved that this is this. It's a contradiction. Now, yeah. So the case we are left with is k is 2 mod 12. K is, let's say, 2 mod 12. Then k looks like 12n plus 2, right? Also, since k is 2 mod 12, we know that 4 does not divide k. Then what? What is then f of I? I did not prove it, but I left it as an exercise for everyone to show that if the weight is not divisible by 4, then f of I is 0. And if the weight is not divisible by 3, then f of omega is 0. And I also said that like this little conjecture that if, let's say, m does not divide k, then f of mth root of unity is 0. This is not actually true. This is true for 3 and 4, but not in general true. Okay. Yeah. Also, here we also have that like 3 also does not divide k. So f of omega is also 0. right? And yeah, and as before, we have that V infinity of f is at least D, right? Like, and here we have D is k over 12 flow. So what is the lower bound of the left hand side of the valence formula? Let's say the valence formula is k over 12 is equal to V infinity of f plus V I of f over 2 plus V omega of f over 3 plus some other things. So this is at least floor of k over 12 plus, well, the order of I is at least 1 since I is a 0. Right? What is the left hand side? Well, I've written k equals 12n plus 2. So the left hand side is n plus 1 over 6. Right? And the right hand side is n plus half plus 1 over 3. Half plus 1 over 3 is approximately, not approximately, exactly 5 over 6. Okay, so this inequality is not true, so we get a contradiction. Wait, what contradiction did we get? No, not n. I did not write it, so like, assume f is non-zero. Then only we can apply the valence formula. Can someone tell me why? Why we need f to be non-zero to apply the valence formula? Yeah, it's zeros everywhere. So the valence formula is not really true because k is a non-zero, well, k is a non-negative number. So yeah. So the left hand side is 0, but the right hand side is non-zero. Right. Also, if f is 0 everywhere, then the order of infinity is actually infinity. So yeah, I should have mentioned it at the beginning. So suppose f is non-zero, then we are applying the valence formula to get all these contradictions. All right, and well, we have a very simple corollary now. That corollary is, let's say f of z is equal to sum of an qn, and g of z is sum of bn qn. And ai equals to bi for every I up to dimension of mk. Yeah. Then f equals to g. The proof is very simple. We just take f minus g. Then the first d coefficients of the f minus g modular form is 0. And as we proved earlier, if the first d coefficients are 0, then that modular form must be 0. So f minus b is 0. Therefore, f equals g. Okay. Yeah. All right. So we have proven a very significant fact that knowing only the first d coefficients are enough. Also, this illustrates a very interesting fact, that is, the first d Fourier coefficients are independent, and the rest of them are dependent. The rest of the coefficients are dependent on the first d coefficients. So yeah, so essentially you can have like any any d complex numbers as the first coefficients, and then yeah, that determines a unique modular form of weight k. This is a very nice result. Yeah, we also have another interesting result about the rationality of the coefficients. And that theorem says that, let's say f of z equals to sum of a n q to the n. And a n is in q for every positive n. Then a0 is also in q. So we have just said that the first d coefficients are independent. And now we are saying that, well, if all the positive coefficients are rational, then so is the first coefficient. So this tells us that, well, although the first coefficient is independent of the next d minus 1 coefficient, the rationality of the rest of the coefficients can give us some information about the first coefficient. It may not tell us about what the value of a0 is, but it tells us that a0 is a rational number. So yeah, that's a very nice insight. So in order to prove it, let's take a slight detour to field automorphisms. So a field automorphism is basically an isomorphism of a field with itself. Okay, and of course a field is where we can add, subtract, multiply, and divide. Of course we cannot divide by 0, but we can divide by everything else in a field. And the nicest field we know is the field of complex numbers. Yeah. Yeah, and there is a very interesting result that suppose f is a subfield of complex numbers. And we have a automorphism of f. Then this automorphism of f extends to an automorphism of c. And this is proved using Zorn's lemma, which is actually equivalent to axiom of choice. So we cannot really write explicitly how this extension automorphism looks like, but we know that it exists. Is it unique? No, I don't think so. Yeah, well, any automorphism of Q is identity, right? Right. I'm saying that if F is an automorphism of Q, then F must be identity. Because all the integers are mapped to themselves. Therefore, yeah, and the rational numbers are quotients of integers. So yeah, so any automorphism of Q is identity, but it has multiple extensions into C. Right? For instance, let's say the complex conjugation, it's an automorphism, right? But yeah, and we have another. What is another example of an automorphism of C? I have it written somewhere. Yeah. Well, identity. Yeah. So these two are like, both of them are extensions of Q to Q, but they're not the same. So it's not unique, but we know that it exists. And although we know that it exists, we cannot write it explicitly. That's the sad part. Okay, yeah. And as we said that the only automorphism of Q is the identity. And we have another very interesting fact. And that fact is, if, let's say, sigma is the automorphism of C, then sigma of a rational number is always a rational number. Okay? And in fact, the converse is also true. What is the converse say? The converse says that if, let's say, x is not a rational number, then there exists an automorphism of C such that sigma of x is not x. So the forward direction says that, well, all the rationals are mapped to themselves. The converse says that the only numbers that gets mapped to themselves all the time. By all the time, I mean that through all the automorphisms, they are only the rational numbers.
Doesn't mean it's not equal to itself. Mean it's not equal to any.
Well, it's an automorphism, right? So it's actually an isomorphism with itself. I'm not going to prove it, but I'm going to just sketch the proof quickly. So yeah, if x is not a rational number, then we have two choices. Either x is an algebraic number or x is a transcendental number. Or x is algebraic. Okay. Well, a while earlier I said that C is the nicest field we know, right? Yeah, I forgot to explain what did I mean by that. The explanation is that, well, C is algebraically complete. That means if we take any polynomial with coefficients in C, the roots are also in C. So that's why I meant by the nicest field we know. Yeah, if X is transcendental, then let's consider the field Q adjoint X. So it's the smallest field that contains Q and the number X. Okay, and this is isomorphic to the field of rational functions over the variable X. Yeah. So, and we can define an automorphism of Qx to Qx by simply defining, let's say, x goes to negative x or even 1 over x. And of course, q have to be preserved, right? And all these terms of qx looks like a polynomial in x over another polynomial in x. So if we know the value of x under the automorphism, then we know the whole automorphism. And if we take x to negative x or even 1 over x, yeah, we get an automorphism of qx. That does not preserve x, right? And we can extend QX, this automorphism, to a automorphism of C. So yeah, so if X is transindividual number, we have a automorphism that does not preserve X. Okay, but what about when X is algebraic? Then what we do is that if X is not algebraic, then it has a minimal polynomial. Right? A polynomial with the smallest degree, whose one of the roots is X. Then what we do is that we take Q along with all the roots of, let's say, the main poly is F. So this is so we are taking Q and all the roots of the minimal polynomial, and then we are taking the smallest field that contains all of them. So it's a field, and what we do is that, let's say if X is a root and X prime is another root, yeah, let's write it like this. Let's say R1 is a root, R2 is a root, and up to Rn is a root. Then we can define an automorphism that takes R1 to R2, R2 to R3, 3 to R4, so on. So and this extends to an automorphism of this field F, and F is a subfield of C, thanks to the fact that C is algebraically complete. So the automorphism of F extends to an automorphism of C. So yeah, you get that. So we have proved that if X is not a rational number, then there is some automorphism that does not preserve X. So using this, we are going to show an interesting fact. And that fact is, as promised last time, that yeah, oh, I stated it. Yeah, let's state it again. An is a rational number for all n, then A0 is also rational. So yeah, so the idea is that we want to show that given any field automorphism of C, A0 stays the same. So that's the main idea. So without loss of generality, we can assume that K is at least 4, right? Because if K is not 4, if K is smaller than 4, then the modular form of weight K is a trivial one. So it has a Eisenstein basis, and we can write F as sum of CAB, E4A, E6B. And the sum is over all the 4A plus 6B equals to K. These are the Eisenstein basis. And also, F is sum of AN Q to the N, right? So let's take, suppose sigma is a field automorphism of C. Then we define R sigma of F. It's basically like taking all the coefficients to their counterparts in the image of sigma. Sigma of AN Q to the N. Now, is it a modular form? Like at the first glance, it looks impossible because, well, sigma is any field automorphism, right? So, and we are claiming that any field automorphism actually preserves our modular form. Yeah, it looks unreal, but actually it's true. Why is this true? Because from this, I can write R sigma of F is equal to sum of sigma of CAB, R sigma of E4 to the A, R sigma of E6 to the B. Right? And if you remember the coefficients of the Q series of E4 and E6, they were all integers, right? In particular, they were all rationals. So R sigma doesn't really change E4 and E6 because field automorphisms doesn't change rational numbers. So these stay the same. And this is the modular form of 8K. So their sum is also a modular form of 8K. Yeah. So now, and what do we have? We have that an is integer for all positive n. So R sigma of f is equal to actually a0 plus, sigma of a0. Sigma of a0 plus sum of an qn, n is 1, is at least 1. Right, because sigma preserves all the ans. And if we subtract it, our sigma of f minus f, we get another modular form, right? And that is nothing but sigma of a0 minus a0. So this is the modular form, and in fact it's a constant modular form. What do you know about constant modular forms? A modular form that happens to be a constant function.
Even
Well, we always have even k. For even k's, a modular form that happens to be a constant function. What is that constant function? 0, exactly. Why is that? Because, well, f of az plus b over cz plus d is equal to cz plus d to the k f of z, right? If f is a constant, this one and this one are the same, right? So if the constant is non-zero, we can basically divide by this and get this is equal to 1 for every gamma, for every matrix in SL to Z. That's not possible. So this constant must be 0. So therefore, this is the constant modular form, implies this is 0. So sigma of a0 equals to a0, and this is true for all automorphism C to C. And what does it tell us? It tells us that a0 is a rational number. All right. Yeah, and last time I promised the theorems, which I'll prove, and we will end today. So that the theorem I promised last time is that zeta of k is a rational multiple of pi to the k. Okay.
also without
Zeta of 3
is rational number.
pi to the 3. Well, the only value of zeta I know is zeta of 2 and 4.
Yeah,
Yeah.
we don't know.
Yeah. And this is for k even and greater than or equal to 8. And yeah, there's a slight side note that is for proving this, we need to know zeta of 2 over pi, so not 2, 4 over pi over 4, and zeta of 6 over pi over 6 are rational. So first we need to know that zeta of 4 and zeta of 6 are rational multiples of pi over 4 and pi over 6. Then using that we can show for all other even integers. Okay. Yeah, can someone guess what? Well, of course, we need to use modular forms. Can someone guess which modular form we need to take to prove this? Hmm? Something related to E4E6. Well, all the modular forms are related to E4E6, right? Hmm? Delta. The delta is a modular form of weight 12. Sorry? Not really. We are taking the modular form of weight k in general. And that is, of course, it's an Eisenstein series, but it's the unnormalized Eisenstein series. So it's GK. Okay, and yeah. And GK is defined as, sorry, we verified the Q expansion of GK, and that was this 2 zeta of k plus 2 times 2 pi I to the power k minus 1 factorial, sum of n equals to 1 to infinity, sigma k minus 1 n q to the n. Right. Oh, we don't really need to know these two, right? Because if we divide by this term, these are all rationals. So this also has to be rational. And this is true even if we don't assume the rationality of zeta of 4 over pi to the 4 and zeta of 6 over pi to the 6. Isn't that right? Yeah, I think so. So let's take gk times k minus 1 factorial over 2 times 2 pi I to the k. Of course, 2 pi I to the k is a real number here because k is even. Is equal to zeta of k minus 1 factorial 2 pi I to the power k plus a sum of sigma k minus 1 of n q to the n. Yeah, q to the n. And we know that these are, well, these are integer valued functions, right? Because these are the sum of the k minus 1th power of the coefficients. So, sorry, not the coefficient. See, the integer. Sigma k minus 1 of n is equal to the sum of d to the k minus 1, where d divides n. So this is of course a natural number. So these are, sorry, yeah, these are rationals. It's a modular form. So by the previous theorem, this also has to be a rational. If this is a rational number, then we are done. So if this is a rational number, then zeta of k over pi to the k, this is also a rational number, which is what we needed to show. Also, I noticed a very interesting fact this morning, and that fact is, yeah. Do you know what zeta of 2 is? It's pi square over 6, right? And zeta of 4 is pi to the 4 over 90. And yeah, and up to zeta of 10, we have pi to the n over an integer. 12 is the first number when it's not an integer, rather a non-trivial rational number. Like up to here we have like pi to the n over some integer, some positive integer. But 12 is the first even number for which I have pi to the n over some rational numbers, not integer. I don't really know what's the significance of this, but there must be some significance. So yeah. So I didn't know about this before this morning. Yeah. Ah, existence of delta. Yeah, and delta was like what, e4 cube minus e6 square over some number, right? Yeah, wouldn't be surprised. Mhm. Yeah, but our like this theorem only tells us that if the first if all the coefficients with positive indices are rational, then so is the first coefficient. It does not tell anything about the coefficients being integer. For instance, we can have all the coefficients integer while the first one is not an integer. Like, can you give me an example real quick? It's E4. In E4, all the coefficients are divisible by 240. In fact, E4 is actually, what is E4? Yeah, E4 is actually 1 plus 240 sum of sigma 3 of n q to the n. If I divide by 240, all these coefficients are integers, but the first coefficient is not an integer. So yeah. Yeah, but I suspect there's some deeper reason behind this. Why 12 is the first number? Yeah, 12 is everywhere in the study of modular forms. Okay, does anyone have any question? We are towards the very end of today's session.
But I've seen modular form in the disk. Is it that you expect?
Yeah. So modular form is a function on the upper half plane. And as we said earlier, we can define it as a function on the open unit disk. And if f is not a modular form but a meromorphic form, then we can no longer define f tilde in the origin. Then we have to define it in the punctured unit disk. So yeah. Yeah, so let's end it today and see you next week.